this. Our big question today is, what is torque and when is an object in static equilibrium? All right. So first thing we're going to look at is the only type of object we're going to look at in this class is what we call a rigid body. The reason is because we have to have something that doesn't deform. That's what a rigid body is. It is an object that does not deform, okay? Because when something deforms, in other words, changes shape externally, then that requires some physics that's kind of over y'all's head, if that makes sense to you. It's very advanced physics. So we're going to look at rigid bodies only. So for a rigid body to be in static equilibrium, that means the object must be in both translational equilibrium and rotational equilibrium. Okay? So what does translational equilibrium mean? We've covered this one already. What does it mean for something to be in translational equilibrium? It has no linear acceleration. This is what we've already done. In other words, the sum of forces is equal to 0. It either has no linear acceleration, which means it's either constant velocity or zero velocity, right? So it's either not moving or it's moving at a constant speed. So what does rotational equilibrium mean? It means it has no rotational acceleration. In other words, instead of forces, the sum of the torques is equal to 0. In other words, the torques clockwise equal the torques counterclockwise. So the clockwise torques are equal to the counterclockwise torques. So it balances. When we look at something like that, let me find it. This would be this guy right here. This guy's in balance, isn't he? Why is he in balance? Because the weight behind this point in his beak is the same as the weight in front of the beak, isn't it? If there were more weight in his tail, which way would he go? Towards his tail, right? Downwards. That would be, for you guys, that would be clockwise, wouldn't it? Now, if there were more weight in his wings, he would dip the other way, wouldn't he? That would be counterclockwise to you guys, right? So that's what we're talking about. For something to balance, it has to be equal weight to either side of its center of gravity, doesn't it? Okay, so equal points wherever. And that's what we look at. So, let's talk about what is a torque. So torque is the measure of the force that makes an object rotate. Okay? And torque depends on two things. First thing it depends on is magnitude of the force. Okay, so how big is the force? And number two, it depends on how far the force is from the pivot. And from the pivot, we're talking about the axis of rotation. Okay? Now, I want you to think about something. When you go to open a door, guys, when you go to open a door, we can do a couple of things here, can't we? Why is the handle to a door so far away from the hinges? That increased distance increases the torque. In other words, it increases the force we can apply to the swing. All right? So when we talk about it, depending not only on how hard I push, but it also depends on how far away from the hinges I push, doesn't it? You ever tried to open a door from the hinges side? It's really hard. I have to push a lot harder to get it to open that much than I do if it's just right here and I just push a little bit to get the same amount of swing. Okay, that's torque. That's what we're talking about, that force that causes it to push. So how big the force and how far the force is from the pivot. So we've got a pivot point. Think of this as the hinges. We've got a distance r from that pivot point, and then we've got a force that's being applied at, guys, this is important, at a right angle to that force, okay? Now this guy right here, this perpendicular line, is called the line of action, okay? And we always look at the force applied at a 90-degree angle. So here's my question. Look at the next example here. So what we get is torque is equal to F times R for this guy, if the force is perpendicular. Now, what happens if the force is not perpendicular? Guess what we're back to again? We're back to vectors. If the force is not being applied perpendicularly, in other words, I'm trying to open the door, but I'm trying to open it at a slant, is all of my force going to be applied to opening the door? No, it's not. You are correct, Reagan. She shook her head. Because you're correct. The only part of the force that's going to be applied is the part that is perpendicular. So how do we find that piece? Well, if you think about it, here's 90-degree angle, right? So this guy right here is going to be and actually, they've got that theta in the wrong place. That theta should be on the other side here. Guys, that theta should be here. We're applying it at an angle, which means theta really should be up here, shouldn't it? Does everybody see that? That theta, the angle at which it's being applied, is being applied to the line of action. That's here. That's this angle. So this guy right here is going to be the force times the sine of the angle it's applied at, isn't it? Isn't that opposite? F is the hypotenuse. So this guy right here is F. Okay? So F sine theta. So now, if we look at this guy, so if it's not perpendicular, to the line of action, then we have the torque is equal to FR sine theta. Okay? If you look on your formula sheet, if you look on your purple sheet, what you will see is the following. You will probably see this formula, or torque is equal to F perpendicular R. Make sense? if you were to look at this in terms of physics C with calculus, those of you who've got a little calculus, torque is equal to the cross product, F cross R, okay? So it is a cross product, which is why you only take that perpendicular. If you remember cross products, we're only looking at 90-degree angles, aren't we? I cross J, J cross K, etc. So only the 90-degree part really counts. Now, direction of path. I want you to look at something though. Look at what this says right here. Only the component of forces perpendicular to the axis of rotation causes the rotation. So even if I'm trying to get something to rotate and I'm pushing on it at an angle, the only part of that force that's trying to cause my hand to rotate is the part that's straight onto it. The part that's 90 degrees to the surface I'm applying the force to. Even if the force is applied at an angle, only the part 90 degrees, the component 90 degrees, causes any rotation. Makes sense, doesn't it? I hope. All right, so the direction of torque. What do we talk about when we talk about torque direction? It's a vector. So the direction of torques are clockwise and counterclockwise. So if we have a counterclockwise torque, that means it wants to rotate which way? Counterclockwise. We want to get it to rotate this way, don't we? That's counterclockwise. This is a positive torque. Clockwise, however, would be applying it this way or this way. So it wants to rotate this way. Clockwise is a negative torque. So this follows the same convention for clockwise and counterclockwise, positive and negative, that angular rotation does. Remember, all angular rotation is positive if it's causing a counterclockwise rotation and negative if it's causing a clockwise rotation. All right, that goes for angular velocity, angular acceleration, theta, all of that. Any questions? Counterclockwise is positive torque, clockwise is a negative torque. So when you're trying to figure out whether or not something has a positive or negative torque, you have to look at the direction the force is going to make the thing rotate, the sum of the torques. Okay? All right, so let's look at this. Torque is a distance relationship. A force applied further away creates a greater torque. Have you ever tried to change a tire? Anybody ever had to change a flat tire? No? Y'all are lucky. I've had to change a flat tire before. If you ever look, the lug nuts on your tires are big, aren't they? And they're put on with what they call a torque wrench, which makes them super tight because you don't want your tire falling off, do you? So when you have to change a tire, you have to break that seal on that lug nut that's been put on with a machine torque wrench. To do that by hand without a torque wrench is really hard if you're trying to do it close up. So instead, you use, if you've ever pulled out your, not your jack, but your lug wrench that comes to your car, it's usually a T-shaped. The lugs are at the very end that fit on the lug nuts on your tire. And then it takes it, that T-shape makes it further away from you. Because the further away we get, we don't have to apply as much force this way, which is perpendicular to the lug nut, isn't it? To get it to break that seal and turn. If we tried to apply the same amount really close to the nut, we'd have to push really hard to get it to go. So instead, we back it away further, okay? It's like with a lever. The further away from something you get, the longer your lever is, the less amount of push you have to put on it to lift something. That's a torque, okay? So if I want to cause something to lift, for me to lift it right here is not super easy, but if I add a lever to it and make it further back, my lever, it becomes even easier to lift. This is acting as a torque. Notice what I'm doing. To get this book to lift up, to rotate, I'm pushing straight down on the ruler, aren't I? I'm putting the torque further away. Now, it didn't take much for me to push here. Here, I actually have to push a lot harder. I want all of you to come and see that. Experience it for yourself. I'm going to put it right here. And I want you to try pushing at the end to lift it, and then try to push it closer. Come on, try it. I want you to experience it so you understand. The further away you push from the point of rotation, the easier it is to cause the rotation. So if you push at the end, pretty easy, isn't it? Now, try pushing up here to get the same thing to happen. A lot harder, wasn't it? Believe it or not, it actually is. You can feel the difference between the two. Okay? Try it. Did you see it was tougher?
Yep.
I know. It seems silly that I'm making you do this, but it really is true. It's kind of stick. You won't break the ruler. It's okay. But it's tougher. All right, so what are the units of torque? I want you to think about it. Torque is what? Force times distance. So what? Yep. Force is newtons and distance is meters. So torque is in Newton meters. Okay? Now, we know something else that is in Newton meters. It's work, isn't it? Joules. Torque does not have any relationship to work, even though they share the same units, okay? Nope, it is not work. I know, it just does not have a relationship. It's one of the worst big mysteries of physics is torque and work aren't the same thing. Torque and work are not the same thing. All right, so let's do some examples here. See if we can figure this out. Bob the builder uses a wrench to tighten a bolt as shown. He applies a 17 Newton force 25 centimeters from the bolt at an angle of 37 degrees with the axis of rotation. Calculate the magnitude and direction of the torque on the bolt. You also understand now why righty-tighty, lefty-loosey works. Think about it. If you're trying to tighten something down, you are tightening it this way, aren't you? Think about why. If you're going this way, it is tightening it down. Think about the right-hand rule. Cross product is the right-hand rule. If we rotate it this way, which way is the force going down? The torque it's going downward, isn't it? So it's helping screw in the bolt, isn't it? Or the screw. So this is taking it downward. So if we want to unscrew it, we go lefty-loosey, don't we? We turn it this way. Think about it. Which way is the torque now going? Which way is my thumb going? Up. So it's helping to bring it back up out of the wood. All right? So righty-tighty, lefty-loosey follows the counterclockwise-clockwise convention. All right, so we know this. We know torque is equal to F perpendicular R, which in this case, it's not perpendicular, is it? So if it's not perpendicular, we need to find the part of it that is perpendicular. All right? So what we need is to draw this in. We need this chunk right here. So if this is 37 degrees, this is also 37 degrees here, isn't it? Think about it. Alternate interior angles. So this is going to be F sine 37 degrees. Okay? So this is F perpendicular. So this is going to be 17.0 times the sine of 37 degrees. So if we're given at it not perpendicular, then we have to do the sine of the angle with the axis of rotation. So now we have to do is plug it into that very simple formula, F perpendicular R. So F perpendicular is 17 sine 37, right? So this is 17 sine 37 degrees times the distance, 25 centimeters. That would be what, 0.25 meters? And then we just work it out. So 17. Make sure you're in degrees. I get 2.6 Newton meters, and don't use it as joules. Never put joules with torque. Newton meters only. Did everybody get the answer? That's a very simple torque problem. Now let's talk about pivot points. If something's pivoting and you've got forces being applied, it says some objects have natural pivot points, but anything can be selected as a pivot point. The value of the torque depends on which point is the pivot. If there is no natural pivot point, in other words, if it's not hooked to something or hanging on a string, if it's not screwed down or hinged to something, that would be a natural pivot point, wouldn't it? If it's not any of those, then pick one of the places where the force is applied or one of the ends. Okay? So, rotational equilibrium. Rotational equilibrium is the sum of the clockwise torques equaling the sum of the counterclockwise torques. That's when it is in rotational equilibrium. Clockwise equals counterclockwise, what you found in your little mini lab, didn't you? To keep it from rotating or changing, you had to put everything to where the clockwise and the counterclockwise torques counteracted each other. So, if it's clockwise and counterclockwise torques are the same about any pivot point, the object will not rotate about that pivot point and is in rotational equilibrium. So if it will not rotate, it's in rotational equilibrium, isn't it? So it says check to see if the object is in rotational and translational equilibrium. All right. So for translational equilibrium, we know the sum of forces has to equal 0, doesn't it? So let's check the sum of forces in the y direction. So the sum of forces here, this guy is up, so that is a positive 12, isn't it? This guy is down, so that is a negative 20. This guy is up, so it is a positive 8. 12 plus 8 minus 20 is what, guys? 0. So check. This thing is in. It is in translational equilibrium. Now we have to figure out whether or not it's in rotational equilibrium. That means the sum of the torques is equal to 0. So we have to figure that out. Now the sum of the torques depends on where the pivot is and whether or not the thing is going to cause it to go clockwise or counterclockwise. So where is my pivot here? This looks like a pivot, doesn't it? So there's my pivot. So the first thing I do to solve these problems is figure out if I applied that force, which way would this thing turn around the pivot? So if I press up on this guy, because that's what this 12 newtons is. So if I press up, is this guy going to go clockwise or counterclockwise? Guys, it's hooked here. This is what your picture looks like. If I press on it here, is it going clockwise or counterclockwise? Well, for you guys, so maybe I should write it this way. So I think this is really what your picture looks like, isn't it? So which way is it going? So it's going counterclockwise. So this is going to make it go counterclockwise. What about B? B is pressing down, isn't it? So which way is it going to turn? Clockwise, isn't it? So this guy's going to make it go clockwise. What about the last point? The one at the end, the 8 newton one. Which way is it going to make it go? Counterclockwise, right? All right. So, sum of my torques, force times distance, right? Counterclockwise is positive, so this is going to be positive, this is going to be negative, and this is going to be positive again, isn't it? Make sense? So let's check them. we have 12 newtons, positive 12 times 1 meter, minus 20 newtons times 2 meters, plus 8 newtons times, I'm sorry, this is not 2 meters, that's 3 meters, isn't it? Excuse me. We got to check the distance from the pivot, don't we? So we've got 1 meter to the pivot here. We've got how far to the pivot? 3. And then how far all the way to the end? All the way to the end, guys, how far is it? 3, 4, 5, 6. So it's 6 meters here. So 20 times 3 and 8 times 6. So 12 times 1 is 12. Minus what? 60 plus what? 48? So what is 12 minus 60 plus 48? 0 Newton meters. So the sum of the torques is 0 Newton meters. So is this thing in rotational equilibrium? Yeah. So does everybody understand how we check for translational equilibrium? We add the forces up. The ones going up are positive, the ones going down are negative. For rotational equilibrium, we add up the torques. The ones that are counterclockwise are positive, the ones that are clockwise are negative. And if those are 0, then it's in rotational equilibrium. All right, simple enough. So let's keep going here. Let's look at another one. We've got a uniform meter stick. Weighs 25 newtons. An 80 Newton weight is hung at the 20 centimeter mark, and 70 newtons is hung at the 90 centimeter mark. So let's draw a picture here. We've got a meter stick. 0 and 1 meter, right? So we've got 3 things we have to look at. The meter stick weighs 25. We have an 80 Newton weight and a 70 Newton weight. So at the 20 centimeter mark, we have an 80 Newton weight hanging down, don't we? Where should I place the mass to represent the meter stick itself? Yep, the middle, the center of gravity, right? So the meter stick is going to be at 50. So at 50 centimeters, we're going to have a 25 Newton weight. And that's the weight of the meter stick itself, right in the middle. And then finally, the 70 Newton weight is going to be over here, isn't it? At 90 centimeters. We've got 70 newtons. So the first thing we have to figure out is what? Is it in equilibrium? Is it in translational or rotational equilibrium? Is it in translational equilibrium? No, it isn't, is it? Because every one of those forces is pointing which way? Down. So it says, what's the magnitude of the upward force needed to balance the meter stick? This would be sum of the forces in the y direction, wouldn't it? In other words, what it's asking you is it in translational equilibrium? So we're going to do our sum of forces. So for part A, we're going to do our sum of forces in the y direction. We have negative 80 minus 25 minus 70. So that gives us what? Negative 175 newtons. So for it to be in translational newtons, the upward force should equal positive 175 newtons, shouldn't it? To balance out the 175 downward. Make sense? So to make it into translational equilibrium, we need positive 175 newtons. Now in part B, it says, where should the force be applied so that the stick hangs horizontally? In other words, where should I put the force so that it hangs horizontally? In other words, so it doesn't do what? Rotate. Now it's asking, part B is asking, how do we get it to be in rotational equilibrium? Make sense? So we need to add up the torques. So the sum of the torques. So what we need to figure out is we're going to have something being applied. So we need to pick a pivot. Do we have a pivot identified for us? We don't, do we? So the easiest place in this case to put the pivot would be right here. So we're going to put the pivot, remember we say it at either one end. If you don't know where it's at, put it at one end or the other. So we're going to put the pivot right here. So we need to figure out, we've got 3 going downward. We need something to counteract it, don't we? So we need some mystery force, and we don't know where to place it. So what we're going to do is the following. We're going to say the sum of the torques has to equal 0, doesn't it? For it to not rotate. So let's add those up. So first things first, is the 80 Newton, let's label these. Is the 80 Newton going to make it go clockwise or counterclockwise? Yeah, clockwise, isn't it? If we have it sitting here and it's pressing downward, all of those are going to make it go clockwise, aren't they? So clockwise, clockwise, and clockwise, which means this other guy, this mystery force, is going to have to go which way? Counterclockwise, isn't it? All right, so let's figure it out. We already know what the force has to be. We know what this force is, don't we? What's the force going to be? We figured that out in the first part, didn't we? So we know this has to be 175 newtons. We just don't know where it's located. So let's do all of the, so we know we have 175 times some value of x, don't we? Because we don't know how far this is. This we do not know. We don't know where it's supposed to be located. Does that make sense to everybody? All right, so minus, the other 3 are going to be minus that, aren't they? Because clockwise is negative, counterclockwise is positive. So we have minus 80 newtons times, where is its location? 20 centimeters, which would be how many meters? 0.2. We're taking the distance, guys. Remember, we're measuring from the pivot. So this distance right here is 0.2. This distance right here is 0.5, and this distance right here is 0.9, isn't it? From the pivot, we measure from the pivot. So, we've got 80 newtons times 0.2 minus 25 newtons times 0.5 minus 70 times 0.9. That all has to add up to 0. So can we solve for x? Yeah. Now, how did I know it had to be somewhere on the other side of the center? We have some weight at the center. We have some weight over here. We've actually got more weight from the center back. The 80 is more than the 70 is, isn't it? On the other side? And the 25 is right in the middle. So doesn't it make sense we'd need some more out here to balance out all the stuff on the other side? Yeah. So what does x end up being? Figure it out. So 80 times 0.2, 25 times 0.5 plus 70 times 0.9 gives me a total of 83.91. Divide by 175, and I get 0.4 what? Did I do 20 or 25? Hold on. 80 times 0.2. I get 0.52. Is that what everybody else got? So 0.52, which is 52 centimeters from the end. Okay? Anybody have any questions about that one? How you guys feeling about it so far? We used both rotational and translational, didn't we? Each time we used both. And for most of these problems, that's exactly what you're going to be doing. Let's look at the last, second to last problem here. An 800 Newton painter stands 3 meters from the left end of a scaffold that's 4 meters long. The uniform scaffold weighs 100 newtons and is hung by a chain at each end. Okay, so draw pictures the first thing. We've got 4 meters long, so this is 0, and this is 4 meters, isn't it? Painter stands, so here's the center. So the painter stands here, doesn't he, at 3 meters? And we've got a chain on both ends. All right. So the first thing you need to look at is what do we have? So let's put our forces in. What type of forces do we have going here? What all forces need to be put on this picture? Think of it as almost like a free body diagram. What forces do we have at play here on the scaffold? Does the scaffold itself weigh anything? The scaffold weighs 100 newtons, so where do we put its mass times gravity? At the center, yes. So the scaffold, the force of the scaffold, force of gravity is here, isn't it? For the scaffold. What about the painter? Does the painter have any mass? So we also have him pressing down, force of gravity of the painter. What other forces do we have here? It's hanging at both ends from what? So if it's hanging from a chain or a rope, what does that cause? Yes, tension. And tension, though, would not be pointing downward, would it? Tension would be pointing upward. So we have tension here, tension on the right end, and here we have tension on the left end. Those are not the same tensions, are they? Think about it. He's standing further to the right, so there's more mass on the right, which means there's more tension on the right. So, where is my pivot? Well, we got to pick a place for the pivot to be. Pick the pivot to be at one end or the other. Where does it make sense for the pivot to be? At 0, yeah. So here we go. Here's my pivot. All right. So now we got to put in all of these things. So this is at 2 meters. This is at 3 meters, isn't it? And there's 4 meters. So first things first, for this guy not to rotate, we need it to be in rotational equilibrium, don't we? So from the pivot, is the tension on the left going to cause any rotation? It can't, can it? Why not? It's being applied, but it's being applied at the pivot. So if I have something here on a pivot, if I push out here, it rotates, doesn't it? If I push here, it rotates. But if I push at the pivot, is it going to rotate? No. So this guy doesn't cause any rotation. These three, however, do. What direction is this going to make it rotate? Clockwise, good. How about this one? Clockwise. But what about this one? Counterclockwise, right? So we have clockwise, clockwise, counterclockwise. So let's label those. Clockwise, clockwise, counterclockwise, because now we can do our sum of torques. We know our sum of torques has to be 0, doesn't it? For this thing to not rotate? Okay, so let's start with the positive one. Tension on the right times the distance is positive, isn't it? And we don't know what that tension is. Minus. Why am I going to do minus? Yep, because everything else is clockwise, isn't it? Force of gravity, it's 100 newtons for the scaffold, so we'll start here. This is 100 newtons. The other dude, the painter, is 800 newtons. So we have minus 100 newtons times, how far away is the center? 2. Minus 800 times its distance from this, which is 3. So we have 2400 plus 200 is 2600 divided by 4. So the tension on the right, if we solve, can we solve this? What is 2600 divided by 4? $650 newtons? Okay. Now here's the cool thing. We've now got the tension on the right. Do you know how we're going to find the tension on the left? What do we know about the sum of forces if it's going to be in equilibrium? So which ones are up? Tension on the left plus tension on the right minus the force of gravity minus the force of gravity, right? We don't know the tension on the left, but we do know right is 650. Minus 100 minus 800, right? So what does the tension on, I don't know why I have equals plus. This should be a plus, excuse me. So what does the tension on the left end up equaling? $250? $250. All right, guys. You have 6-2 homework exercises to do. 6-1 and 6-2 are due next time. Make sure you're caught up. You're going to finish your test in the first 15, 20 minutes. We're going to go over, I'm going to check homework, go over it. Remember, we're in the last 9 weeks and we don't have much left. So do all your homework, okay? All right. Stay caught up. Oops.